One of the major goals of this course was to be able to describe the motion of an object. To do this, we developed the vector quantities of linear displacement, velocity, and acceleration, and derived a series of kinematic equations to describe motion with constant acceleration. We then introduced the concept of force and analyzed the motion of objects with dynamics and Newton's laws of motion. In the previous chapter, we once again developed the concepts of displacement, velocity, and acceleration, but this time for rotational motion. This led to another set of 5 kinematic equations that are completely analogous to the kinematic equations for linear motion, where the linear variables x, v, and a are replaced by theta, omega, and alpha. Now we turn to the dynamics of rotational motion. In other words, what is the rotational analog of force? Linear accelerations are produced by forces, but rotational accelerations are produced by torques. Torques cause rigid objects to rotate about an axis, and the magnitude of the torque depends not only on the magnitude of the force applied to the rigid object, but also on where the force is applied relative to the axis of rotation. Think about a heavy door that is free to swing on hinges attached to one of its sides. This defines the axis of rotation for the door. The figure shows a top view of such a door and different ways that a force could be applied to the door to open it. Although equal forces are applied to the door in each case, the magnitudes of the torques produced are different. Qualitatively speaking, it is easier to open a door when the force is applied farther away from the axis of rotation. It's no mystery why door handles are usually located toward the far end of the door away from the axis of rotation. Specifically, the force applied farther from the axis produces a greater torque. However, the angle at which the force applied is also important. In panel C, we apply the force as far from the axis as we can, but it is directed in toward the axis of rotation. For this situation, the torque on the door is actually 0, and it won't rotate at all. This next figure shows a similar situation with an overhead view of the door. We now want to define some important concepts associated with torque. First, we have the line of action. This is an extended line that is drawn collinear with the force. Next is the lever arm L, which is the distance between the line of action and the axis of rotation, measured along a line that is perpendicular to both. Torque is then defined as the following. The magnitude of the torque, represented by the Greek letter tau, is equal to the magnitude of the applied force times the lever arm. The vector nature of torque is handled the same way as with the rotational kinematic variables. The torque is positive when the force tends to produce a counterclockwise rotation about the axis, and negative when the force tends to produce a clockwise rotation. The SI unit of torque is the Newton meter. Notice that the magnitude of the torque not only depends on the magnitude of the force, but also on the length of the lever arm. It's often convenient to write the torque in terms of the distance between the axis of rotation and the application of the force, usually labeled r. Based on the geometry in the figure, we see that the lever arm is equal to r sine theta, where theta is the angle between r and F. Thus, we can write the torque as torque equals F times L, which equals F times r sine theta. This offers a couple of advantages. First, we see that for a given force, the torque will be maximum when r is as large as it can be, and when the angle is 90 degrees. Second, the torque will be 0 if r equals 0, which means the force is applied at the axis of rotation. You know from experience that you can't open a door by pushing on its hinges. And finally, the torque will also be 0 if theta is equal to 0 or 180 degrees. In this case, the force is applied directly toward or away from the axis of rotation. During our study of linear motion, we considered the equilibrium situation when the sum of the external forces acting on an object equaled 0. In the next section, we will consider the rotational version of this equilibrium. In other words, when the sum of the external torques on a rigid object is equal to 0.